Somewhere inside an IBM lab this spring, a research team asked an AI a simple astronomy question. Which of the giant planets in our solar system have rings? The AI, a full-scale language model built by Meta, got it wrong. It said only Saturn has rings. Then the researchers ran the exact same model through a quantum computer, changed almost nothing about it, and asked the same question again. This time, it answered correctly. Jupiter has rings, Saturn has rings, Uranus has rings, Neptune has rings. All 4 gas giants correctly identified for the first time. Nothing about the model's core knowledge changed. What changed is that somewhere inside that answer, a quantum processor had quietly done something classical computing alone could not do on its own. And that tiny, almost unglamorous moment might be one of the first pieces of hard proof that quantum computers can make artificial intelligence smarter in ways raw computing power cannot. If that sounds too small to matter, stay with me, because the size of the fix is exactly the point. This was not a supercomputer curing cancer or breaking encryption. It was a research team proving something far more specific and, in some ways, far more important. That you can take a massive AI model already trained the conventional way, route a tiny sliver of its reasoning through a real physical quantum processor, and get answers back that the model literally could not produce on its own. Not faster, not cheaper. Actually different. Actually better. And the scientists behind it say this is the first time anyone has demonstrated that kind of quantum enhancement on a production scale, real-world language model running on actual quantum hardware. Not a simulation, not a toy example, the real thing. To understand why this matters, you first need to understand the wall that modern AI is currently running straight into. Every large language model you have ever used, every chatbot answer, every AI-generated summary, all of it is built by scaling up. More data, more computing power, and above all, more parameters, which are essentially the internal dials and knobs a model tunes during training to get better at predicting the next word in a sentence. GPT-5. 5, one of today's most advanced AI models, is estimated to run somewhere between 2 trillion and 5 trillion of these parameters. Every single one of those parameters has to be stored somewhere, processed somewhere, and powered by real electricity in a real data center. The bigger the model gets, the more infrastructure it demands, and at some point, that curve simply cannot continue forever. You cannot keep doubling parameter counts indefinitely without eventually running into physical limits on power, cost, and hardware. This is the exact same infrastructure crunch that has been driving the AI industry's obsession with ever larger data centers. And it's the reason researchers everywhere are hunting for a different lever to pull, one that doesn't just mean building bigger. It's worth sitting with just how strange that scaling problem actually is once you look closely at it. Doubling a model's parameter count doesn't just double the cost of training it. Training runs for the largest models already consume electricity on a scale that rivals small cities, and every additional generation of frontier models has needed exponentially more computing infrastructure just to squeeze out incremental gains in accuracy. Researchers across the industry have openly acknowledged that this brute force approach is running into diminishing returns, where each new leap in parameter count buys a smaller and smaller improvement in actual capability. That's precisely the environment in which a result like this one lands with so much weight. If a technique exists that can extract meaningful accuracy gains from a model without adding meaningful size, cost, or energy demand, it doesn't just matter to a handful of quantum physicists. It matters to an entire industry that is quietly worried about whether the scaling strategy that got AI this far can keep working for much longer. That is where quantum computing enters the picture, and not in the way most people expect. For years, the popular pitch for quantum computing and AI has been about speed. Quantum computers process information using qubits instead of ordinary bits, and unlike a bit, which is locked into being either a 0 or a 1, a qubit can exist in a blended state of both at once, a property called superposition. Pair that with entanglement, where the state of one qubit becomes linked to another regardless of distance, and you get a machine that can explore a staggering number of possibilities simultaneously instead of working through them one at a time. That property is exactly what makes quantum computers so good at certain kinds of optimization and simulation problems that would take a classical supercomputer years or centuries to grind through. But this new research is not really about speed at all. It's about accuracy. It's about whether quantum computers can make an AI model's actual reasoning better, not just its raw processing time faster. Here is exactly what the researchers did, and I want to walk through this carefully because the method itself is the real story. The team, from a company called Multiverse Computing, started with Llama 3.1, an 8 billion parameter language model built by Meta and used widely across the AI industry. Multiverse Computing isn't a household name the way IBM or Google is, but inside the smaller world of quantum software companies, it has built a reputation specifically around this kind of hybrid work, using quantum techniques to compress and optimize classical AI models rather than trying to build an entirely separate quantum AI from scratch. That distinction matters because it shaped the entire approach here. Rather than asking whether a quantum computer could someday replace classical AI infrastructure, the team asked a narrower, more immediately testable question. Could a quantum computer improve a model that already exists and is already deployed without retraining it from the ground up? They didn't touch the model's original training. Instead, they built small mathematical structures called Cayley parameterized unitary adapters, or CUAs for short. Think of these as small, specialized correction modules. The team trained these adapters using ordinary classical computers first, tuning them the normal way. Then, instead of running those adapters on a regular chip, they loaded them onto an actual quantum processor, specifically IBM's Quantum System 2, a real physical superconducting quantum computer built from 156 qubits. The model's original 8 billion parameters stayed completely frozen and untouched. Only this tiny quantum-enhanced adapter layer was added on top, and the entire system was then run end-to-end, meaning the quantum hardware was actually involved in producing the model's final answers in real time, not just assisting in training beforehand. The results, on paper, look almost absurdly small, and that smallness is exactly why the researchers say it matters so much. To understand why perplexity is the metric that matters here, it helps to know that it's one of the standard yardsticks used across the AI industry to measure how well a model is functioning at its most basic task, predicting the next correct word or token in a sequence of language. A model with lower perplexity is, in a very real sense, less confused. It assigns higher confidence to the correct next word more consistently, which tends to translate into fewer hallucinations, fewer wrong answers, and generally more coherent output across everything the model does. It's not a flashy number, but it's one researchers trust because it can be measured precisely and compared directly between two versions of the same underlying model, which is exactly the comparison this study needed to make its case. Adding this quantum-trained adapter layer added only about 6,000 new parameters to a model that already had 8 billion. That is an increase of roughly 750 thousandths of 1%. An almost invisible rounding error in terms of size. And yet, that microscopic addition lowered the model's perplexity by 1.4%. Lower perplexity means a more accurate, more reliable model. To put it plainly, the researchers made the model meaningfully better at its core job by touching a piece so small it barely shows up on a spreadsheet. And the piece that made the difference had to run through actual quantum hardware to work. Now, here's the part that should genuinely make you sit up, because the researchers themselves were careful, almost cautious, about how they framed this. In their own published paper, uploaded to the Physics Research Archive in early May of this year, they wrote that the significance of their results isn't really about how big the improvement was. A 1.4% drop in perplexity is not going to replace a $1 trillion AI industry overnight. What matters, in their own words, is that measurable quantum enhancement of a real, deployed, production-scale AI model exists at all, running on real quantum hardware, doing real work, producing real, verifiable, correct answers a classical-only version of the same system could not produce. That distinction between the size of an effect and the mere existence of an effect is exactly how every major scientific breakthrough in history has started. Small, deliberate, carefully measured proof that something impossible on paper actually works in a lab before anyone tries to scale it up. And scaling it up is precisely where this gets interesting for the future of AI as an industry. Right now, quantum computers are still what physicists call noisy, meaning they are extremely sensitive to interference from their environment, from stray electromagnetic radiation, temperature fluctuations, even naturally occurring cosmic rays passing through the hardware. Every one of those disturbances can flip a qubit's state or scramble a calculation before it finishes, and unlike a classical bit, which is robust enough to shrug off almost any stray interference, a qubit's delicate quantum state can collapse from something as small as a nearby Wi-Fi signal. That noise is the single biggest obstacle keeping quantum computers from tackling much larger, more ambitious problems today. Aizpurua explained that this is exactly why his team kept their quantum adapters so small in this experiment. The bigger a quantum circuit gets, the more noise creeps in, and the more likely the whole calculation collapses into meaningless garbage. Keeping the adapters tiny was a deliberate choice to work within what today's imperfect quantum hardware can actually handle reliably. As quantum processors get less noisy and more powerful over the next several years, the size and complexity of what these adapters can do is expected to grow substantially, and with it, potentially, the size of the accuracy gains. This is also exactly why IBM's own long-term roadmap matters here. IBM has publicly stated its goal of building what it calls Starling, which the company describes as the world's first fault-tolerant quantum computer, meaning a machine advanced enough to correct its own errors faster than they occur, effectively eliminating the noise problem that limits today's quantum hardware. IBM's target date for Starling is 2029. If that timeline holds, the kind of tiny, careful 6,000 parameter quantum adapter demonstrated this year could plausibly become something dramatically larger and more capable within just a few years, not decades. The researchers behind this study aren't claiming they've already reached what physicists call quantum advantage, the point where a quantum computer does something meaningfully useful that no classical computer could ever do at all. What they are claiming is that they found a real, working, measurable foothold on the path toward it, inside an actual production AI model, not a laboratory toy problem, invented purely to make quantum computers look good. It's worth being honest about the limits here too, because a good story doesn't need exaggeration to be genuinely exciting. This was one study on one specific model using one particular architecture of quantum adapter, tested on a relatively narrow set of benchmark questions. A 1.4% drop in perplexity, while real and independently measurable, is not the same as saying quantum computers are about to make every chatbot on Earth dramatically smarter next year. The researchers themselves describe this work as a proof of concept, a foundation for future development, not a finished product ready to be dropped into ChatGPT or Claude tomorrow. And there's a deeper unresolved question sitting underneath all of this too. Right now, only a small adapter layer is being run on quantum hardware, while the model's actual core parameters remain entirely classical. The next serious research challenge, according to the team itself, is figuring out how to encode much larger portions of a model's reasoning directly into quantum circuits, not just a small corrective layer bolted on afterward. That's a significantly harder problem, and nobody currently knows exactly how long it will take to solve, or whether today's leading quantum hardware architectures are even the right ones to eventually get there. There's also a fair question worth asking about how much of this improvement could eventually be replicated on a classical computer using a similarly small, similarly clever adapter, without any quantum hardware involved at all. The researchers don't claim to have ruled that out entirely. What they do argue is that the specific mathematical structure of the Cayley unitary adapters relies on operations that map naturally onto how qubits behave, and that the quantum hardware gave them access to a particular kind of transformation that would have been considerably more expensive, though not necessarily impossible, to approximate purely classically. That's a more careful, more scientifically honest claim than saying quantum computing did something classical computing could never do under any circumstances, and it's exactly the kind of claim that tends to hold up better under scrutiny from other researchers trying to reproduce the result. But step back for a second and look at the shape of what just happened, because the shape matters more than the size. For years, the conversation around quantum computing and artificial intelligence has mostly lived in the future tense. Someday, quantum computers will help train AI faster. Someday, quantum computers will solve optimization problems that make today's models more efficient. Someday, someday, someday. This is one of the first times researchers have taken that someday and turned it into a specific, documented, independently verifiable result sitting on the physics preprint archive right now, in a form other scientists can actually go check for themselves. A real 8 billion parameter model, a real 156 qubit quantum processor built by IBM. Real questions the model got wrong before and got right after. That is a meaningfully different kind of claim than another projection about where quantum computing might be headed in 10 years. It also quietly reframes something important about how the AI industry has been thinking about its own future. The dominant strategy across the entire AI industry right now is simply to build bigger models, bigger data centers, bigger training runs, bigger electricity bills. That strategy has worked remarkably well for years, but it runs headfirst into physical limits eventually, limits on power availability, limits on chip manufacturing at capacity, limits on the sheer cost of training ever larger systems. What this research quietly suggests is the outline of an entirely different lever nobody has been able to reliably pull before now. Instead of making models bigger, you make a microscopic sliver of them smarter, using a kind of computation that operates on principles no classical chip, no matter how large, can replicate. If that lever turns out to scale the way the researchers hope it will as quantum hardware improves, it wouldn't just be an efficiency trick. It would be proof that the ceiling on how good an AI model can get isn't only a function of how much classical silicon you're willing to buy. Think about what that actually implies if the trend holds. Every major AI lab today is locked into essentially the same race: spend more, build more, train longer, and hope the next model is meaningfully better than the last one. If quantum-enhanced adapters like this one keep improving as quantum hardware matures, an entirely different kind of AI lab becomes possible, one that doesn't necessarily need the biggest data center to build the most accurate model. It needs access to a sufficiently advanced quantum processor and a clever enough adapter design. That's a very different competitive landscape than the one the AI industry has been operating inside for the last several years, and it's exactly the kind of shift that tends to sneak up on an industry slowly, one small published paper at a time, until suddenly it doesn't look small anymore. This also lands at a moment when quantum computing as a whole has been racking up milestone after milestone that would have sounded like science fiction just a couple of years ago. Google's Willow chip has already demonstrated a specific verification algorithm running thousands of times faster than the best classical supercomputers could manage on the same task, a result Google described as a genuine, verifiable quantum advantage rather than a theoretical projection. Researchers at Aalto University in Finland recently published a new quantum algorithm capable of solving a previously intractable materials science problem in a matter of seconds, rather than the years it would take classical methods. Work that appeared in the peer-reviewed journal Physical Review Letters and was specifically flagged by the editors as a notable advance in the field. Separately, IBM's own hardware has recently posted its highest fidelity calculations sustained over the longest period ever recorded on one of its processors, another quiet but important sign that the error rates plaguing quantum hardware are trending in the right direction. None of these results, including the AI enhancement study, are claiming quantum computers are ready to replace classical infrastructure across the board. What they are collectively showing is a steady accumulation of specific, narrow, real, reproducible wins, each one chipping away at the assumption that quantum computing is still purely theoretical. This IBM and multiverse computing result simply happens to be the one that lands closest to something almost everyone reading this has personally used: a large language model answering a question. So where does this actually leave us? Quantum computers did not replace AI this year, and they are not going to next year either. What happened instead is narrower, stranger, and in some ways more convincing than a headline about quantum supremacy. A team of researchers took a real, widely used AI model, added something almost too small to measure, ran it through an actual quantum processor, and watched it answer questions correctly that it had gotten wrong moments before. Small effect, real hardware, reproducible result, published for anyone to check. That's not proof that quantum computing has solved artificial intelligence. It's proof that it can, in a very specific and carefully documented way, make artificial intelligence better at being right, using a kind of computation classical chips fundamentally cannot perform. And if the pace of quantum hardware improvement over the next few years matches even a fraction of what companies like IBM are promising, that tiny 6,000 parameter foothold could turn out to be the first visible edge of something much bigger. If this story surprised you as much as it surprised the researchers who ran it, follow along for what happens when quantum hardware finally scales up enough to test this for real.